According to the National Electrical Code, specifically Section 250.104 the number 4 copper connection to a concrete encased electrode is required to be made within the concrete itself. Leaving a portion of the rebar exposed and sticking out of the concrete for connection is not permitted. The code mandates that the connection must be made to the reinforcing steel that is embedded at least 6 inches or 152 millimeters into the concrete. This requirement ensures a reliable and effective electrical connection to the grounding electrode system. Section 250.104A3 specifies that the concrete encased electrode must be at least 20 feet, or 6.1 meters, in length and must be embedded in the concrete for minimum length of 30 inches, or 762 millimeters. These dimensions are crucial for the electrode to function properly as part of the grounding system. An exposed or buried section of rebar does not meet the criteria for a concrete encased electrode connection as defined by the NEC. The primary reason for these requirements is to ensure a consistent and reliable electrical path to ground. When the connection is made inside the concrete, the moisture and chemical composition of the concrete help to maintain a good electrical bond between the rebar and the surrounding earth. This is crucial for dissipating fault currents and providing a low impedance path for ground fault current to return to the source. In contrast, exposed rebar is subject to corrosion and oxidation, which can significantly increase the resistance of the connection. This increased resistance can impede the flow of fault current, potentially leading to dangerous voltage levels and increasing the risk of electrical shock. Additionally, the exposed rebar may not be in direct contact with the earth, further reducing its effectiveness as a grounding electrode. The NEC guidelines are designed to minimize these risks and ensure the safety of electrical systems. Therefore, it is essential to adhere to the specific requirements for concrete encased electrode connections. The proper installation involves making a secure connection to the rebar within the concrete, ensuring that the connection is protected from corrosion and that it meets the minimum embedding depth and length requirements. Failure to comply with these regulations can result in code violations, safety hazards, and potential damage to electrical equipment. The grounding system is a critical component of any electrical installation, and the concrete encased electrode plays a vital role in providing a reliable path to ground. By following the NEC guidelines for installation and connection, electricians and installers can ensure the safety and effectiveness of the grounding system and protect against electrical hazards. Therefore, always make sure that the number 4 copper connection is made inside the concrete, adhering to the specified embedding depth and length requirements. Avoid using exposed or buried rebar as a connection point, as it does not meet the code requirements and can compromise the integrity of the grounding system. Doing so ensures compliance with the electrical codes and the safety of the electrical installation. The code specifically addresses grounding electrode conductor connections. These conductors connect the grounding electrode, such as the concrete encased electrode, to the electrical system's grounding busbar. The connection must be accessible and securely made, using listed connectors suitable for the purpose. Furthermore, the connection should be protected from physical damage. The purpose of a grounding electrode system is to provide a low impedance path for fault current to return to the source, thereby facilitating the rapid operation of overcurrent protective devices, such as circuit breakers and fuses. This rapid clearing of faults minimizes the risk of electrical shock and equipment damage. A properly installed and connected concrete encased electrode contributes to the overall effectiveness of the grounding system, ensuring that fault currents are safely dissipated. Incorrect grounding electrode connections can have several negative consequences. Firstly, they can increase the impedance of the grounding path, slowing down the response time of overcurrent protective devices. This delay can increase the duration of fault currents, leading to higher touch voltages and greater potential for electrical shock. Secondly, poor connections can generate heat, which can further degrade the connection and potentially lead to a fire. Thirdly, non-compliant installations can result in code violations and potential liability in the event of an electrical incident. Therefore, meticulous attention to detail is required when making grounding electrode connections. It's vital to use appropriate connectors, follow manufacturer's instructions, and ensure that the connections are securely fastened and protected from environmental factors. The number 4 copper conductor is commonly used for connecting to the concrete encased electrode due to its suitable ampacity and resistance to corrosion. However, the specific conductor size may vary depending on the size of the service entrance conductors. The NEC provides guidelines for determining the appropriate grounding electrode conductor size based on the size of the service entrance conductors. It is important to consult the appropriate tables in the NEC to ensure that the grounding electrode conductor is adequately sized for the installation. In addition to the concrete encased electrode, other types of grounding electrodes are also recognized by the NEC, including ground rods, ground plates, and metal underground water pipes. Each type of grounding electrode has its own specific installation requirements. The selection of the appropriate type of grounding electrode depends on site conditions and the overall design of the electrical system. In some cases, multiple grounding electrodes may be required to achieve the desired grounding impedance. The NEC provides guidance on the installation and connection of multiple grounding electrodes. For example, if ground rods are used, they must be spaced at least 6 feet apart and bonded together with a grounding electrode conductor. The purpose of bonding multiple electrodes together is to create a more effective grounding system and reduce the overall impedance. The concrete encased electrode, often referred to as a UFA ground, is considered one of the most effective types of grounding electrodes due to its large surface area and intimate contact with the earth. The concrete surrounding the rebar helps to maintain a consistent moisture level, which further enhances the conductivity of the electrode. This makes the concrete encased electrode particularly well suited for locations with dry or sandy soil conditions. When installing a concrete encased electrode, it is important to ensure that the concrete mix is of sufficient quality and that it is properly compacted around the rebar. Air pockets in the concrete can reduce the effectiveness of the electrode. Therefore, it is recommended to use a concrete vibrator to ensure that the concrete is fully consolidated around the rebar. Furthermore, the rebar should be free from rust and corrosion before being embedded in the concrete. Any rust or corrosion can increase the resistance of the connection and reduce the effectiveness of the electrode. The NEC also addresses the use of supplementary grounding electrodes. A supplementary grounding electrode is an additional electrode that is installed to augment the primary grounding electrode system. Supplementary electrodes are often used in situations where the primary electrode does not provide sufficiently low grounding impedance. For example, a supplementary ground rod may be installed near a sensitive electronic equipment to provide a dedicated grounding path. The installation of supplementary grounding electrodes must comply with the requirements of the NEC. It is important to bond the supplementary electrode to the primary grounding electrode system to ensure that they function together effectively. The NEC also covers the grounding of metal enclosures and equipment. Metal enclosures and equipment must be grounded to provide a low impedance path for fault current to return to the source. This grounding helps to protect against electrical shock and equipment damage. The grounding of metal enclosures and equipment can be achieved by connecting them to the equipment grounding conductor, which is typically a green or bare copper wire. The equipment grounding conductor runs with the circuit conductors and connects to the grounding busbar in the electrical panel. The NEC provides specific requirements for the size and installation of equipment grounding conductors. It is important to consult the NEC to ensure that the equipment grounding conductors are adequately sized and properly installed. In addition to grounding, bonding is another important aspect of electrical safety. Bonding involves connecting together all metal parts that are likely to become energized during a fault. This creates an equipotential plane, which helps to minimize voltage differences and reduce the risk of electrical shock. The NEC provides specific requirements for bonding metal parts, such as metal water pipes, gas pipes, and metal building frames. It is important to follow these requirements to ensure the safety of the electrical system. The NEC is a comprehensive document that covers all aspects of electrical safety. It is updated regularly to reflect changes in technology and industry best practices. It is important for electricians and installers to stay up to date with the latest version of the NEC to ensure that their work complies with the code. Continuing education courses and professional certifications can help electricians and installers stay informed about the latest changes to the NEC. Electrical safety is a critical concern, and following the NEC guidelines is essential for protecting against electrical hazards. A properly designed and installed electrical system can provide years of safe and reliable service. By paying attention to detail and adhering to the requirements of the NEC, electricians and installers can contribute to the safety of their communities. In conclusion, the NEC mandates that the connection to a concrete encased electrode be made within the concrete, with the rebar embedded at least 6 inches or 152 mm deep. Exposed rebar is not an acceptable point of connection. Adhering to these guidelines ensures a safe and effective grounding system, minimizing the risk of electrical hazards and promoting the reliable operation of electrical equipment. This system is essential for safety. Remember that the concrete encased electrode should be at least 20 feet or 6.1 meters long and embedded at least 30 inches or 762 millimeters in concrete. It is the responsibility of all electrical professionals to understand and follow these requirements to protect lives and property. Therefore, it's essential to strictly adhere to the specific requirements outlined in the NEC for concrete encased electrode connections to ensure a safe and compliant electrical installation.